Let me see you folks do one now. Let's come over to the other board. Log base 10 of 1,000. Log base 10 of 1,000. Sarah? I'll help you. Exponent, what's the exponent of 10 that gives you 1,000? 3. Good. Okay. Leah, you want to try one? Sure. Okay. Log base E of, making it more exciting, huh?
All right.
E to the 5th.
Would just be 5.
It's 5, right. What's the exponent of E that gives you E to the 5th? Okay. Not too bad, is it? Okay. So, let's see what else we could do. I want to do one more with the base 10. And then I want to draw the graph of the base 10 logarithm. Because this is very important. This one is used a lot. The Richter scale for earthquake intensities is a logarithmic scale. The hearing decibel ratings are logarithmic scales. Go to a really loud rock concert and the sound is up around 120 decibels. You go to a duck game at Autzen Stadium, the sound level is up close to that. Not too far off from what the intensity of a jet engine near, as a plane comes in for a landing over you and you're right there near where that plane's coming in, or plane taking off, jet engine taking off. That sound intensity is up there around 120, 140 decibels. Those are logarithmic scales. pH in your shampoo, pH balanced shampoo, that's a logarithmic scale. pH is the hydrogen ion concentration that exists in something. It's a measure of the acidity or the alkalinity of the substance, the material. You eat a tomato, it's got a little bit of acid taste to it. A lemon, similar, okay? Those have a pH value that is less than 7. They're acidic, okay? What do you clear a plugged drain in your bathroom sink with? Either a plunger is a mechanical way of trying to do it, but you also can put something like Drano in, sodium hydroxide, which is an alkaline type of substance that'll eat the gunk that's in your trap of the sink drain, and has a different pH. It's way above 7. 7 is considered neutral. Okay, we'll talk about those things a little bit later. Earthquake intensity, decibel ratings, and pH kind of things. Okay, let's do one more base 10 logarithm. Log base 10 of 10,000. Answer, Todd? 4. What's the exponent of 10 that gives you 10,000? 4. Now, what is really interesting about looking at these numbers right up here on the top, the base 10 logarithm, is you should immediately, just like your basic family of graphs that you've already learned, when you see logarithm, you should immediately think of the graph. I would encourage you. And so this is going to be a base 10 logarithm, which means that it comes up off this asymptote, goes through 1, 0. In other words, the log base 10 of 1 is 0. Input is 1, output is 0. And you have to go out how far to be up 1? Good. You have to go out to the base to get, here's the base's value. You have to go out to the base to be up to a value of 1. Now, how far out do you have to go to get up to a height of 2? Here's 1. There's your 1. How far out do you have to go to the right to be up to a value of 2? You have to go out to, Melissa, 100. Let's see, if this is 10, if this distance right here is 10, then 100 is about halfway over to the far wall to just get up to 2, right? And to get up to a height of 3, look up here, to get up to a height of 3, you have to be out to 1,000.
What is that?
1,000, that's out in the hallway. Okay? And to get out to up to a height of just 4, I have to be clear out at 10,000.
Out of the building.
10,000 is 1,000 times 10. So if I went 1,000 times this distance that way, I'd be clear off out of the building to be up just to a height of 4. So what you can observe from this is that when you see large changes at x, large change in x on logarithms, you usually see a very small change in y. Small change in y. If you take a Richter scale for giving us a rough estimate of the intensity of an earthquake, if you have a Richter scale intensity of 6, that's a pretty good shake. I was in college and high school in Los Angeles, and I was in a couple pretty good ones. And that's pretty unnerving when all the land around you starts moving and the building you're in or whatever starts shaking and things start flying. Okay, earthquake intensity of 6. If you go from an earthquake intensity of 6 to an earthquake intensity of 7, the amount of intensity, the intensity of the earthquake has, the energy that's been released is 10 times as much. 10 times as much energy release. So it's a base 10 logarithmic scale. A magnitude 8, like the severe shakes like that have occurred near 8 up in Alaska and out in the Pacific, that's 100 times a 6. Okay, so logarithmic scales base 10, they change as multiples of 10. Multiples of 10. Okay. So you have to go, this thing really goes out fast and it rises very slowly. Okay, that's important. Let's look at a couple other things and then we'll start doing some practical problems in the time that remains today. Let's look at a logarithmic equation. As you've noticed, every time you master something in math, we give you something new that sort of scrambles your brain a little bit. And then it takes a lot of practice on your part to get good at that new item. And then we give you something else. Okay, so just be aware. Anybody taking chemistry this year right now? Are you playing with logarithms at all yet?
Oh, yeah.
Oh, yeah. For pH and other types of things like that? Yeah. Okay. Okay. Let's look at let's think of a graph for a second. Log base 3 of x. Draw a quick sketch of that. If you're watching the DVD, pause it for a second, draw a quick sketch. And label at least 3 points. Label 3 points on the sketch. Time's up. Okay. So, the graph looks like this. There's 1 point labeled. Somebody want to give me another point? Max?
3.1.
3, 1, right?
3.1.
Perfect. And another one, somebody?
9.2.
9.2. Great. Sounds like you're listening. That's good. Okay. 9.2. Okay. Domain? Look at the picture.
0 to infinity.
Not including 0, though. Greater than 0, right? Range? All real numbers, right? Negative infinity to infinity. Good. Everybody okay with this? All right. Try this. On that same sketch, let's draw this. 1/2. 1/2 is in here in front in my writing. It's kind of messy. 1/2 logarithm base 3 of x plus 2. What does the 1/2 do to the graph?
Smush it.
Squashes it, makes it half as tall. The heights, see here are your heights, these values. These are your outputs. Are made half as tall. So here's my little code I like to use. And, careful, this is inside, messing with the input. You're messing with x.
Or left. Move it.
Left 2. Go back and think about the circles we did at the very beginning of the course. How, if you had an x plus 2 quantity squared in your circle equation, the circle center shift and the whole graph is shifted 2 to the left. So the sketch of this thing then is going to be taken 2 to the left. What happens to this vertical asymptote here? It goes with the shift, doesn't it? It goes with the shift 2 to the left. So you take it 2 to the left, you label it as a vertical asymptote, and then you take your graph and bring it 2 to the left. And if you're taking and multiplying the heights, if you're distorting the thing first by making it half as tall, what's half of 0? Half of 0 is still 0, isn't it? So that point just simply gets shifted 2 to the left. That's important. So minus 1, 0 is your 0 of the new graph. Now I've got a tricky question to ask you. Tricky question. We were out here at 3 and up 1 on the basic logarithm graph, weren't we? Where does that point go to on this new graph? 3, 1 becomes what?
1 and 1/2.
Becomes what?
1 and 1/2.
1.
2.5.
1.
Got 2.
No, Jennifer, let me go with Jen. You go ahead. What do you?
It's,
What x value?
it's a half.
A half for the x value?
The x value is 1,
X value is 1
and the y value is a half.
right here.
Yeah.
1 comma 1/2. Does anyone else agree?
Is that right?
Melissa and Leah agree? Okay. So let's check it. If you took this graph and made it, if you made this graph half as tall, there it would be at 3 and 1/2 in height, first of all. And then you take that point and move it 2 to the left. 1, 2, right on. Looking good. Everybody agree with that? So what happens then is this graph is going to have similar character, and it goes out looking like that, doesn't it? And you'd have to go out to what value to be up at 2? Well, actually, I'm sorry, not 2. If you went out here to 7, if I went out here to 7, my scaling's getting off here. If I went out to 7, it would be up at 1, wouldn't it? Sorry for being so messy here. I'm going to redraw this in just a second. So the picture, the final picture here, we would want to fairly neatly draw it. It would be like this, x equals -2. And it would go through this point, and it would go through 1 and 1/2. And then it would go through out at 7, it would be up at 1. And we get a nice looking picture looking like that. And that's the graph of y equals 1/2 log base 3 of x plus 2. How can I check what I just drew? How can I check with what I just drew? I can drop these inputs in and see what I get. Drop the inputs in and see if I get, drop in a -1. If I drop in -1, can I fit it on here? Yes, f of -1, let's see what we get. We get 1/2 of the log base 3, put in a -1 here of 1, right? And what's log base 3 of 1? What's the exponent of 3 that gives you 1? What's the exponent of 3 that gives you 1? 0. That's a 0 right there. And so we get 0 as a result here. That's this point right here. Let's try putting an input of 1 in. Input of 1. I get log base 3 of 3 with a 1/2 in front. What's the exponent of 3 that gives you 3? That turns to 1, and we get a value of 1/2. And if I put a 7 in, f of 7, checking this point, 7, 1, I'm checking it. Putting that in, 7 in here makes this 9. 1/2 of log base 3 of 9. The exponent of 3 that gives you 9. I want you to be able to say that as easily as I do. Of course, I've been doing this for years, okay? But that's the objective. What's the exponent of 3 that gives you 9? That's a 2. 2 times 1/2 is 1. Checks, 7, 1. Okay? So what you do is, this is nothing more than transforms that we've learned earlier. If you understand your fundamental graph, you should be able to sketch this thing fairly quickly and answer the questions like what the domain and the range is. What other point would be a good one to plot on this picture?
Y-intercept.
The y-intercept, always. And y-intercepts are usually easy, aren't they? Because we let the input be 0, right? So let's find that y-intercept. And so we're finding f of 0, and so we're going to have the 1/2 of the logarithm base 3 of 2. Now think about this value mentally. What's the exponent of 3 that gives you 2? I have to scratch my head on that one. What's the exponent of 3 that gives you 2? It's got to be smaller than 1, doesn't it?
1/3.
Doesn't it have to be smaller than 1? But it has to be bigger than, what's the exponent of 3 that gives you 2? Has to be bigger than 0, but less than 1. Has to be trapped somewhere in between there. Okay? Now, look at the picture. Look over here at the picture. If you look at the picture, you can see that here's your height of 0 back here. And when you get clear out to +1, you're at a 1/2. So somewhere in between here, we're going to have to be, somewhere in between 0 and a 1/2 is where that value is going to have to be. Are you ready to tackle doing that? Figuring that out? Not quite. We have to learn a little bit more about logarithms before we can exactly answer this question, precisely answer this question. Okay, so we're kind of left in limbo for a moment. Okay, keep that kind of question in the back of your mind, and what I want to do is go tackle some of the other properties now of logarithms. We've got some properties related to the graphs here. We've got some properties of some examples of how to determine where certain key points are, and we've also seen a little bit with transformations. But let's go look at some of these other properties for a minute.